Hello everyone. So I am a PhD student at Indian Institute of Science. I am pursuing my PhD in representation learning. So this week we will be discussing about the week two contents, and we will be solving the previous year or some questions from the previous lecture contents. So first of all, in the week two, we are gonna cover some of the revision of the concepts that uh, have already been covered this week. So it will be based on the Sigmoid neuron, gradient descent, and the universal approximation theorem. So I hope that you might have went through the lecture series and attempted the questions in advance before joining the session. So I will be just revising some of the concepts before solving some problems. And then after the revision, we will be just solving one by one problem. And if any of you have any doubt, feel free to ask. Okay, so let's get started. So I will be referring the material for this week for you to have some revision. And if you have any doubts or any questions, feel free to ask. So firstly, about the week one recap. Okay, so what we talked about in the week one. So I will be just recapping some of the concepts. And then we will be moving forward to the week two. Okay. So as of now, in the week one, we were talking about the Boolean functions. So what are the Boolean functions? So basically, any function we know, it's of the type normal. This is the normal type of any functions. That is, we have a function f whose domain is whose domain variable is x, and the range is a y, basically, where x is my domain and y is my range. So it can be different orders or something. It does not matter because in the multivariate calculus, it can be of higher order, or in the simplest case, it is just a scalar quantity. Okay. So in the Boolean case, x only can take the value 0 to 1. Okay. 0 and 1, not 0 to 1 exactly. It can either take 0 or either take 1. So out of the two only, it can take the values. Okay. And the output in the simplest case also belongs 0 to 1. That's it. Either the output will be yes or no. That's the binary thing. So whenever you heard of a Boolean functions that takes a variable x, and each variable will be either on or off, and the combined decision of the different variables will be giving a decision of yes or no. Okay. So this was what we have done as of now. Okay. But so that was the Boolean function. Then we talked about the perceptron. So the perceptron was a very simple model which was trying to fit the normal Boolean functions, set of Boolean functions basically. So you might have remembered that we had something like this. We are x1, x2, xn, and each of them, that is xi, belongs to 0, 0, 1. It's a set. That's why I'm writing in the curly bracket instead of a normal closed and open bracket. Okay. Then it gives the decision output, and here it was the bias term. So the output was just y was 1 or 0. If it will be the 1, if my summation wi xi is greater than equal to some bias term. Okay. Otherwise, it will be 0. So it was a very simple model. Then we talked about the learning algorithm. So it was used for the classification task. So we had suppose two clusters. Then it can be means using this algorithm, you can find the separating hyperplane. So separating hyperplane in this case, because our data is a linearly separable, we can find the separating hyperplane, which can distinguish between the different classes. Okay. And we looked about the simple learning algorithm that how to run this weight to take a proper decision. So that was the story of the week one, basically, in the short. Okay. But now coming to the very natural case which arises in the means everywhere. Okay. So basically, as I mentioned, now we will be covering week two. Okay. So week two content, I will be just going through whatever was there in the content. Okay. And we are gonna solve the problems afterward because it's necessary to have a recap of the concepts so that if you are lagging anywhere, I can help you out. So in the week two, suppose we know that a function y is f of x. So this is the normal function. In the usual case, x can belongs from Rd in the usual case. Last time it was just 0 and 1. That's why we were calling it as a Boolean function. And also the y can be R, where R is my set of reals, that is minus infinity to infinity. Okay. So basically, how can we run this type of a function? The question is that. Okay. And that's a more general case, which arises in usually a regression task. Okay. So the natural question which arises in the last time we saw that if we have a different clusters which are linearly separable, then our model using the new normal neuron, we can able to find a separating hyperplane. Okay. But now the case is different as our x is a whole real range. So the now natural question which arises, can we have neural network which can approximate any function? Okay. So this is the normal question which will be arising. Okay. So our function usually in the 1D simple case, I will be taking my x belongs to R, y belongs to R. So we have a bunch of functions. Okay. So bunch of functions in the sense our function can be something like this. It can be like this. It can be like this. Something it can be in the 1D case where this is my x and this is my y. So the question is, can we approximate any function of this type? Any function it can be sine, cosine, tangent, okay, e to the power minus x, log x, something, any, it can be a combination of these two or anything, okay? So how do we means approximate this function using a neuron? And what are the fundamental quantities that a neuron should satisfy in this case? So this are some of the questions which arise. Okay. So we will be looking, means I will be just explaining the things which in the upcoming upcoming time. Okay. So as of now, the first thing is that the perceptron we had, it has a drawback. Can anyone tell me that what was the drawback basically? So okay, so basically I think the normal drawback if you see is that our decision we were making some decision that either it should be 1 or 0 based on certain quantity W naught. So it was like this in the perceptron thing. We were making a decision. Okay, was either 0, 1 or 0 based on certain condition, or the condition in the sense if it is greater than W naught, where W naught is our bias and something like that. Okay, what does it means physically mean mathematically? That what does it convey? That how the decision is getting made. So firstly, suppose this is my W naught in simple case. Okay, so it was suggesting that if my certain condition, if it's greater than W naught, then our decision is gonna be 1. Otherwise, it's 0. Okay. So this was the decision-making process which was happening in the perceptron. So each neuron will be taking a decision based on a certain activation, and that activation is very harsh. If you see, some what are the different properties of this function? You might have seen come across this function a lot of time. Okay, this is called as a step function. Okay, and the thing about a step function is that it is not differentiable at W naught because there is a sharp rise and the left hand limit does not equal to right hand limit. Okay, that's why it does not exist. At differentiable, the left hand limit should equal to right hand limit should equal to function value. Okay, so that's the differentiability part basically we have. But in a lot of cases, this condition was, as I mentioned, it is very harsh. What I mean by the harsh is that suppose if I move a little bit forward, then the decision is 1. And very little backward, then the decision is no. So it's kind of a, in the nature, usually whatever we deal is continuous functions. Everywhere if you see the wind, the flow of wind, normally if, it's common example. If you go to a beach and there's a rate of flow of air, basically you will feel hot when cold breeze near the sea. Sorry guys. So if it is very much kind of a continuous thing, continuous in the sense if you go inside the beach, means inside water near the beach, there you will feel some flow of air. But if you come outside on the beach on sand basically, then also you feel, but somehow the air quality will be decreased. So it's kind of some certain changes are there, but that is not very much abrupt. It's not like that there is a cold breeze over the ocean and nothing basically over the sand. Okay. So nature deals with the continuous functions basically. The rate of change is properly defined. It's not a very harsh. So as I mentioned about the decision making process and what are the certain disadvantages. So that's what was covered in this week thing. Now we will be talking about what we want. Okay. So the next thing is from perceptron to sigmoid neuron. Okay. So we will be moving forward from perceptron to the sigmoid neuron. Okay. So sigmoid function, I guess some of you might means have heard of this. What are the sigmoid functions? Okay. So basically, if you see the decision making we were having, it was very harsh. Harsh in the sense and W naught, the decision was y. It was 1 and 0. But what we want basically is that the decision should be something like this. And this function, I guess you have came across a lot of time, but yeah, I will be just telling you that what this function is. Okay. This function is basically the properties. If you see, it's firstly continuous, secondly differentiable. Okay, that's what we wanted basically. We want the function to be continuous, differentiable, smooth. This is what we want. But the now question arises is that how can we convert, get this kind of a functional form? So one of the very common form which you will be seeing is that here the decision Z was taking as of the form like this. I from 1 to n. Okay. Now our decision in this case, now we want to have a smooth function. So one of the way is there are a lot of approaches in which you can get a smooth function like this, but we will be taking a very simple approach. Okay, that's how the functional form is. Okay, so we can have something like this. As our decision is between 0 and 1, on or off. Okay, so basically something like this we can have. So this is what we call as a sigmoid function. Now, suppose one fundamental question I will be asking, what's the limit of this function as minus infinity and infinity? So limit x tends to infinity 1 divided by 1 plus e to the power minus x. So what it is? As x tends to infinity, e to the power minus x tends to 0. So in this case, it is equal to 1. Okay. And the limit x tends to minus infinity 1 plus e to the power minus x. In this case, we are having e to the power minus x, and x tends to minus infinity. Minus of minus infinity is positive infinity, and positive e to the power any positive infinity quantity is again infinity. So 1 divided by infinity is 0. So this limit is basically 0. So this function is well defined over the range. So over from minus infinity to infinity, the values taken by this function is 0 and 1. That's what we wanted. Okay, that was the main goal. And somehow we are able to accomplish with this type of function. Okay, now how do we take a decision based on this? The question is that. So basically, we in this form we will be having decision of something like this: 1 plus e to the power minus w naught plus summation wi xi ranges from 1 to n, depends upon the dimensionality of the input features. So there isn't any sharp turn basically in this case, and the function is very smooth. The limits are well defined. It is differentiable. Why we need differentiable, I will be discussing now, but little bit later. That differentiability plays a very important role. In deep learning, basically, you want everything to be differentiable. Okay, as much as possible. Basically, differentiability is some criteria which you want. It is the first side, sometimes the first order differentiability, sometimes second order differentiability. Okay. And the output 0 to 1 in this case gives the probability of success. So basically, it's our function is like this. This difference gives the probability of, means what's the success rate. That's what we want. Okay, either it can be 1, 0, or zero point 0.9. So how much it's far or closer to being a decision at what? Okay. So now question arises is that how does this looks like? So we have a sigmoid neuron sigma where we give inputs x1, x2, xi, w1, w2, wi, which gives output y, which is in the range of r. In this case, it's of subset 0 to 1. Okay. And also we have a bias term W naught, which is people usually take as per the notation theta minus b. So it depends upon the different literature. Now the question is, we have a new kind of a neuron which can operate in the minus infinity to infinity input range, and which can give us the output of 0 to 1. But how do we run the weights? Because to take a decision, we need to run the weight. Means the last time it was very easy, but here the question is that in this case, how do we run it? So in simple word, I will be giving one common theme across, which is common across the deep learning community. Okay. Deep learning community or any kind of a black box modeling, what people does is that we have we have an input x size where I can range from 1 to n. That is a sample point. Okay. We need to predict y I. So it's I'm talking about supervised. Supervised in the sense we have an input feature, we have an output feature. So later in the course, I guess we will be covering something unsupervised as well. Okay. So we will be covering that as well. Now, this is what's the real data is that there is underlying mechanism, underlying function F, which we don't know. That's what the deep learning is all about. To find, we have our input samples, we have a labels for that, but the function, how the input is getting flow towards the output, we don't know. That function we want to approximate. So that approximation we does using a neural network. Okay. So I hope this point is clear. So we have an input unknown function f, which describe that how each input is getting mapped to the output. Okay. And once we settled it, then how do we run the parameters? Okay. So as of now, this function f we parameterized it by theta, where my theta is set of all weights. There might be a confusion regarding the misconception about the theta variable, but it's just a learnable parameters which take input xi maps to the yi cap, the prediction output. And there is an underlying function f which gives yi. So we have having a prediction. We are having a truth. Using this two, we want f theta to learn about f. That is, f theta should be as close to f. This is the task. Okay, we are having a prediction. We are having a ground truth. We want to predict that how these two are correlated. So usually we define a loss function. Okay, it can be described mathematically as R cos R to R. So it's a function. Basically, a loss is a function which take a prediction, that is yi cap and yi, and it is split out a number. Okay, it gives some number, suppose loss, and this loss we want to minimize. This is can called as a loss, error, mismatch, a lot of terminologies, but basically in deep learning, error. Or so this is the signal. Signal in the sense this is kind of information we are having, which we want to use for a model to learn about the underlying function f, which we are parameterizing it by function f theta, where theta are the set of weights which are learnable. Okay, I hope this concept is clear what I'm telling. Okay, now one thing about the perceptron algorithm was just wait. Sorry for the disturbance, guys. So yeah. So the perceptron deals with only the linearly separable data, that it can run the weights on the my data is separate. That is, I have certain data of this form. Then it can run the weights basically about different hyperplanes separating each class. But the thing is that in the nature, this kind of a data finding is hard. It's not easy. Okay, all of the data is not of this type at all. You will be finding data in the form of like this. In this case, what's the best hyperplane? How can you describe it? Because it's you can't separate it. The perceptron is useless in this case, basically. But we can also have a lot of separating hyperplane, which tries to distinguish between the different classes. But the question is, out of this thing, which is best? Okay, best in the sense it try to classify the as much as possible the different classes properly. Means the truth and the difference, the loss of this thing is minimized. So we are gonna be picking some model f theta, okay, which minimizes this quantity. That will be the best thing. That's what we want. It's all about finding a model having a very less loss. Okay. So basically, in the form, in the sigmoidal form, we have been given the data of the form xi, comma yi, where I is ranging from 1 to n. So this is the data we are having, and we need a model y. It predicts y cap, which is of the form sigmoid neuron 1 plus e to the power minus w transpose x. Okay, or you can simply write it as y cap is equal to w transpose x. This approximation. We are doing approximation here for classifying. Okay, or we can have something like this: y cap is equal to x transpose w x, where x is my input, and this all really should work until unless we make sure that w transpose x is a scalar quantity. W is my a vector, x is my a vector. Okay, now we need to run this w basically. Find this find we used usually by we need to find this parameter w, the optimal, and that optimal parameter w star is done by minimizing the loss y cap, comma y. Okay, and to minimize this function, we use gradient descent. Okay, so a lot of things is going on. We have an input, we have an output, we have underlying mechanism function, which we don't know, and we need our algorithm to learn about the underlying function f by minimizing the loss function, which we need to learn the parameter optimal parameter w star. Okay, which we learn to the uh, gradient descent algorithm. Okay, guys, give me 2 minutes. One. Okay, so let's set this problem that what is our objective? Let's take an example for that. We have a training objective. We have been presented with the data xi, yi, where I is ranging from 1 to n. We want to find a weight w, b, okay, which minimizes. We want to run this. Basically, this will be our optimal w star and b star, which is a summation of I equal to 1 to n yi minus f of x. This is our normal squared error loss. Okay. So it's trying to measure the amount of deviation between the predicted and the truth and squaring it. Why we are squaring it? Because sometimes it can be positive and negative, and in the whole summation will be getting means what I say getting nullified. So basically, you can't the loss function is already minimized in that case. So that's why we want a positive quantity. And second thing is loss, we want it to be differentiable. Okay. So, so I guess in the weak lecture, you might have seen the how to find a W star and B star optically. Okay. So I will be taking once means I will be deriving its algorithm pointwise. Okay. That how you can learn it. So basically finding a brute force method of W star and B star, what's the best method we can have? Okay. So basically it's like the loss curvature. You might be in the lecture series. It can be like assumed like this. We are having a W star, W and B. We are I'm plotting its contour plot. Okay. Suppose you initialize the W and B somewhere here. Okay. You know the optimal point is here. But you can't guess it. Means here it's simple because you know. But how can we have certain algorithm which can take us from any initialization position and to the minimizer of that particular contour? So that's where the gradient descent comes. Okay. So it's about we know at a particular point. So at each particular point in the parameter space, you can have certain ball. Ball in the sense you can draw a small ball and you can try to take a random direction and try to take one direction which minimizes. But is it optimal? Can anyone answer this? The answer is it's a NP hard problem because the amount of direction you are having is very large. It is exponentially grows. But that's not a feasible solution at all. But can we do better? Better in the sense an algorithm which can ensure that every time we are decreasing the function, means minimizing our objective. The objective value, what it was, the loss between the truth and the prediction. So it's like this. We are being in the parameter theta. We need to alter it. Alter it means we need to go move little bit further. Okay. We need to take a step del theta and we need to basically update as theta plus del theta is equal to theta prime. And we need to ensure that our L theta prime is less than or equal to L theta. That's how the minimizing, it should be a monotone sequence. If it's not a monotone sequence, you can't ensure the convergence. Convergence in the sense that with the probability one, you are almost sure that you are gonna be reaching at a particular minimum, that is W star optimal point. So this is how we will be constructing a sequence. We will be constructing a sequence W1, which is an initial point, theta2 till theta n. And our theta one n star, theta for optimal will be theta n. And this sequence should be monotonically monotone in the term that L theta I plus 1 is always less than or equal to L theta I. If you can have a L theta less than, that's what we want, but less than or equal to sometimes it's not necessary because you might be in the flat minima and you might be stuck in there. So ideally speaking, you should not have you should make sure that after the objective is decreasing sufficiently. Okay. Now the thing is how fast you should move. Basically, suppose you are moving across a straight line. Okay. This is a road basically. You are here basically. You know that you are driving a car basically here. Okay. You want to reach here, but in first time you are means driving on this road, suppose. But how much the speed you should have here? Means suppose you saw this because you can see only the vertical thing. You are not sure that how the road is diverging after that particular point. So you should control the speed in such a way that you reach here rather than going and bursting here. So that's how you make your decision. So that's what we need. So basically, we have been given theta, del theta. So instead of using all del theta, that's the change what we want. We are gonna update it using eta. Eta is my learning rate. So there's a huge literature about the learning rate, how you can regulate it and ensure that you reach the minima. Okay. So theta ensure that this theta is between 0 to 1 in most cases. So this will be our theta mean. Okay. The question is that theta nu is equal to theta plus eta del theta. Okay. So del theta means we don't know at particular point that what's the best del theta is. Okay. So what we can do is that there comes the handy Taylor series. Okay. So Taylor series we are gonna be using. We want to ensure that our objective is getting decreased after taking a small step eta times del theta. So basically we want e theta plus eta del theta. So if you expand the Taylor series around theta, okay, so it will be L of theta plus eta del theta transpose, okay, L theta, L, sorry, my mistake. So it's of the form del theta L of theta. Del theta L theta will be dimension of theta only. That's the point to be taken care. This whole quantity is a scalar, means a number, because a loss function gives you the signal of a scalar only. Okay, that's something of order eta square, which we avoid it basically because eta is between 0 to 1. Eta square will be very less quantity. So we usually avoid that in the deep learning. We want to make algorithm as simple as it is. Okay. So now L theta plus eta del theta. You can rewrite it as this thing. Okay. This is this quantity. We want it to be negative. Why negative? Because we want to ensure that there is a sufficient decrease in the objective value. Okay. There is a sufficient decrease in the objective value. So we need to find this del theta in such a way that there is the decrement should be a large decrement. So how it can be the large? We want to maximize this, means minimize this quantity. Okay, we want to minimize. How can we do that? We have a two vectors. Okay, so this thing you can write it as two vectors, and we know about two vectors the quantity. If we have a vector A and B, then A dot B divided by A, norm of B gives you cos theta. This we know. Okay. What does this imply? And the cos theta, the range of cos theta is between -1 to 1, which implies that del theta transpose gradient of L theta divided by norm of del theta, norm of gradient of L theta is bounded above by 1 and bounded below by -1. Okay. This quantity, okay, this is what we got as of now. Okay. Now this quantity, we want to find del theta. Okay. So basically, this is the angle. So my means you can rewrite it as above by norm of del theta, gradient of theta. This is what we want. Okay. Now the upper bound and the lower bound we have. Okay. As I mentioned, we want to minimize this quantity. Okay. When it will be getting minimized, when this quantity is getting equivalent to this, when my both the are in the same direction, means in the opposite direction. See, del theta, L theta. This is the direction of this thing. Two vectors, their dot product achieves the lowest bound when the angle between the two vectors is 180. So our del theta transpose, means our del theta should be basically in the backward direction of where my gradient is pointing. So basically my del theta should be minus del theta of transpose. So this is what we got. Okay. So it's called a gradient descent because the gradient gives us the ascendant vector. Descent in the sense we are gonna go in the direction opposite to the gradient. So direction opposite to the gradient. Okay, I hope this point is clear. That's why it's called as a gradient descent. I hope this point is clear. Okay. So now you are familiar with this stuff. Okay. I will be doing one for the perceptron algorithm, that for one point dominance for perceptron, that how this learning is happening. Okay. Basically, in the perceptron algorithm, in the sigmoid algorithm, where our range is data is from minus infinity to the infinity, and the range is between 0 to 1. It's of this form. Okay, so it's of the form this thing. The simple case I'm taking one dimension, but same thing goes for external case, which is of the RD dimension. Okay. Now our loss function is a function of L and P. We can write the square error loss for one data point only. This one data point is easy. F of x minus y squared. Now I want to calculate the gradient of this loss function with respect to w. Then I can rewrite it as 2 star 2 f of x minus y del w f of x. Okay, this 2 gets cutted. Follow the steps what I am doing, and if you have any question, do let me know. Okay, so I have simplified it. Now the one tool in the calculus, the fundamental tool, we are gonna be using it to calculate this gradient thing. Okay, we need to calculate this thing. This quantity is already well known. We know that what it is, f of x minus y. Okay, so to take a gradient of this thing, so let's take. Okay, so I hope this point is clear. As same, I have written it here. Now the quotient rule. Whenever you have p by q, how you differentiate it? That rule we are gonna be using it. So it's just simply square of it. Okay, because it's if my it's p by q, then I write it as q p prime minus p q prime divided by q square. Okay, then it's equivalent to e to the power minus wx plus p minus x. So this is how it will get simplified. Firstly, take a derivative. That's why square is coming. 1 is 0. Okay. So minus p, it's coming, and q. The derivative of e to the power minus x is e to the power minus x. Okay. E to the power anything is e to the power that thing. Then the differentiate e to the power that function, that then take a derivative of that function thing. Okay. You can simplify it as f of x 1 minus f of x 1 minus f of x into x. So there is some algebraic steps which I have missed. So you need to do the algebra between how we got from the student. Okay. If you have a doubt, you can just refer to the notes. Okay. So I guess till this point it's clear. Okay. And so now let's go on solving some problem statement. Okay. Some problems. Let's have a 1 minute break before that. Okay. Then I will be after 1 minute, maybe. Okay, welcome back again. So let's solve some problems. So total 10 problems I will be solving today for the session. If you have any doubts, feel free to ask. Okay, so let's start. So the first question is we know the sigmoid function, which is of the form 1 divided by 1 plus e to the power minus x. The question is range of sigma x. Okay, so basically we need to find that what is the range of values that sigma x. So in my previous, just before now, this problem solving, I have discussed this, how to approach this problem. You need to see the limits point, asymptotic behavior, that is the minus infinity and infinity, and take a zero. You will get how the function is behaving. That's the one thing you can do. And second thing is double differentiate function. If it's double differentiation, if it's positive, always for all values of x, then the function is either increasing only when it's monotonically increasing, otherwise the function will be monotonically decreasing. So let's see how this function looks like. Okay. So first way of using this is plotting. That's many of you will find it easy. At 0, what's the value we know? It will be 1 divided by 1 plus e to the power minus 0. E to the power minus 0 is equal to 1. So that is 0.5. Okay. Now, this function, the limit x tends to infinity, 1 divided by 1 plus e to the power minus x. As x tends to infinity, e to the power minus x tends to 0, and 1 plus, so it reaches what it is. It's 1. So 0.5 it is. We know the asymptotic behavior is that as x tends to infinity, it is 1. Similarly, as x tends to minus infinity, it's 1 divided by 1 plus e to the power minus x. E to the power minus of minus infinity is equal to e to the power infinity. 1 divided by e to the power infinity is equal to 0. The function looks like this. The range of this function, the sigma x, is always between 1 and 0. So that's what's the first question. The answer will be B for the first question. B in the sense 0 to 1. Now the second question is, what happens to the output okay, what happens to the output of a sigmoid function as mod of x is very small? So it is based on the previous question as well. Okay, so there is a connection between these two stuff. Okay, so what it is? Function, you know, was something like this. Okay. Now mod x. What's the function of mod x? Mod x equal to x if x is greater than or equal to 0, minus x if x is less than 0. So sigma x from minus infinity to 0, it takes values between 0 to 0.5. So it is asking about mod of x. Just talking about this thing. Nearby mod of x is less than means it's nearby to 0. You got the logic, what I'm telling. Okay. So the sigmoid function behavior around 0 is what it is. The output sigma x is equal to 0.5 such that mod of x is very equivalent to 0. So the nearby behavior. Okay. So that was the second question. Now the third question. Okay. The third question is about which of the following theorem states that neural network with a single hidden layer containing a finite number of neurons can approximate any continuous function. So this is the question. I hope you are familiar with the answer. The option, suppose I gave you base theorem, you know what's the base theorem, P of A given B, think, okay, that, so it's not a base theorem. The second option is center limit theorem, that random variable, the sum of random variable divided by n converges to a Gaussian random variable, okay? So the expected value is, so that is also not the answer. Fourier theorem, okay, so Fourier theorem is also not the answer. The answer for this question is basically universal approximation theorem. Okay, now coming back to fourth question. We have a function f. Okay, so basically we want to approximate this thing, triangles. So I guess this was covered in the lecture content. Totally 150 towers are there. How many neurons we need? You got the question. We want to approximate 150 towers in the 1D. How many neurons is needed? The answer is any function, any tower can be approximated as using of this tower one, the difference of this tower. So if you subtract the two functions, you're gonna get a tower. So each tower needs 2 neurons. Okay, so total 150 will be needing. 150 will be needing 300 neurons. Plus one neuron which aggregate all the neurons output. The answer for this is 301. Coming back to fifth question. So it's like this. We have a two input neuron, two hidden there, each consisting of 5 neurons. And output is having a 3 neurons. Input, output, hidden. So how many weights are there? You know they are connected like this. Okay, so the answer is 5 cross 2. Okay, plus 5 cross 5 plus 5 cross 3. You got the point? Permutation. We're talking about we had having in the first input 2 neurons. First, there are 5 neurons. Total number of weight between these two is 5 to 10. 2. That is 10. This is equivalent to 10 plus 25 plus 15, which is equivalent to 50 neurons. Okay. So that was the question. Now coming back to sixth question. Question is about radio activation. So let me tell you about what this activation is. Sigma of f of x equivalent to x if x is greater than or equal to 0, 0 if x is less than equal to 0. So it's like this. It's 0 if my x is negative and is equal to x if my x is positive. So it's talking about what's the derivative of this function. That is del delta x at 0. So first of all, the left hand limit and the right hand, it's continuous. Okay. But the limit left hand derivative is 0, right hand derivative is 1. 1 is not equivalent to 0. So it's not differentiable. So answer is okay. Now coming back to seventh question. Consider a function f of x, which is of the form x cubed minus 3x squared plus 2. Okay, just talking about gradient descent. Okay, eta is equal to 0.1. Initial x value is 4. Third iteration we need to find x3. Okay, so first of all, let's calculate f dash of x. That is 3x square minus 6x. You can write it as 3x x minus 2. Okay. Update formula is x1 is equal to x naught minus eta. Eta is equal to 0.1. Initial point is 4. Add that particular 4. 3 cross 4. 4 minus 2. x1 equal to 4 minus 0.1. 3 to the 12. 12 to the 24. 24 into 0.1. 2.4, so that is equivalent to 1.6. Okay, so that's the after first iteration. The second iteration, x2, it will be 1.6 minus 0.1, 3x 4.8, 1.8 minus plus. It will become plus. Okay, 1.6 minus 2, 1.6 minus 2 minus 0.4. If you calculate it, it's 1.6 plus 0.1 into 4.8 into 0.4 is equal to 1.6 plus 0.192 is equal to 1.79. This is the value after second update. Now the third update we need to do the x3. It is again x2, that is 1.79 minus 0.1. What was the 3 into 1.79? 1.79 minus 2. Okay. The answer will be coming around. I am leaving up to you to solve this. Either you can use calculator or add by hand. So I'm not going to solve the numerical equation for this. You need to do it. It will be plus 0.112. The answer you should be getting is 1.9. Okay. So that was the seventh question. Coming back to question 8. Okay. Which of the following statement is true about representation power of multi-layer neuron with sigmoid function? The first question, the thing is a multi-layer network of sigmoid neurons can represent any Boolean function. A multi-layer network of sigmoid neurons can represent any continuous function. I hope you would have got the answer. The answer is basically the second one. The first one is not a Boolean. does any continuous function. Sigmoid neuron, you make a multi-layer network, and then you can approximate any continuous function. Okay. Question number 9. How many Boolean function can be designed for 3 inputs? That's a pretty tricky question. The number of Boolean function we need with 3 input. Okay. So basically, my function is there. Okay. 3 input are there. Okay. So firstly, for the 3 inputs, how many different combination can be there? It's 2 to the power 3 because it's either 0 or 1. Okay. Total 8 kind of input variations are there. Okay. Now for each variation, it can either give 0 or 1. The amount of permutation will be, in that case, 2 to the power 8, which is 256. You got the logic. We are having a 3 neurons, each with the value 0 or 1, either 0 or 1. So the number of combinations we can have is 2 to the power 3, that is 8. And with the 8 different input functions, you can have, for example, for one of them 1, rest of them 0. So how many different combinations such a way? 2 to the power 8. Now the last question. How many neurons do you need in the hidden layer of the perceptron to run any Boolean function with 6 input? Okay. So the question is how many neurons we need to run Boolean function with 6 input. Each perceptron 0 or 1. So basically the number of combination of input is 2 to the power 6, that is 64. So only one Boolean function is given. We want to run any one Boolean function. So how many neurons you will be needing it? That is 64, 2 to the power n, because okay. So that was all for the today's session, I guess, if you don't have any more doubts or anything. So I'm pausing as of now. So if you have any question, you can ask.